Good afternoon to all. So next topic is speed control of DC motors. So in practical applications, motors may be required to perform number of desirable jobs or operations, conforming different load conditions and speed requirements. Okay, so the motors have to perform a number of desirable jobs at different load conditions for the required speed. So the availability of the DC motor to adjustment of their operating speed over wide ranges and by a variety of methods is one of the important reasons for strong competitive position of DC machinery in the industrial applications. Okay, so DC motors are widely used in the industrial applications. Why? Because of their wide range of operating speeds, okay, by variety of methods, by different methods at different speeds we can use DC motors. Therefore they have a strong competitive position in the industrial applications. So the nature of the speed control required for different industrial drives are the variable speed drive, multi-speed drive, and we can even call as creeping speed drive. Okay, means if I say variable speed drive, these drives require a continuously variable speed over the range from 0 to full speed. Okay, such drives are, we will call them as variable speed drives. Okay, so the variable speed drives will be requiring continuously variable speed over a wide range from 0 to full speed. And if you go for multiple speed drives, these drives will require only 2 to 3 fixed speeds over a region. Okay, and creeping speed drives will be having a speed which is needed for adjusting or setting up the work on driven machine only for few revolutions per minute. Okay, so whenever we want to adjust the speed or setting of certain job or work driven on a machine only for few revolutions per minute, such speeds we will call it as creeping speeds, and the drives in which creeping speed is there, such drives we will call it as creeping speed drives. So let us go for the next topic, that is types of loads. Okay, so whenever we are selecting a motor, okay, we must before selecting the motor we must know its characteristics, isn't it? We have already discussed its starting characteristics and load character and running characteristics we must know. Okay, so whenever we are selecting a motor, in addition to the information of this load, speed, torque characteristics, okay, the variation of how load and torque are varying. So what are all the losses that occur in this motor, and how the temperature is raised, means when the motor is running, how the temperature raises. What is the raise in the temperature in the motor with respect to time? Okay, we must also consider these factors. Okay, so while selecting a motor, not only the characteristics that are to be considered, but how the load torque varies, okay, under running condition, and how what are all the losses that occur, and how the temperature will raise with respect to time. Okay, so with respect to time, load variation, torque variation, how the losses are, what are all the losses, and temperature raise must be considered. Okay, in case the load and torque with respect to time variation is periodic and repetitive, Okay, if the load is varying with respect to time periodically, and if it is repetitive, and torque also, which is varying with respect to time, is periodic in nature and it is repetitive. Okay, such one cycle of that load with respect to time and one cycle of the torque with respect to cycle or duty cycle. Okay, one cycle of that load which is periodic and repetitive, or torque which is periodic and repetitive. Okay, each cycle we will call it as load cycle or duty cycle. Okay, so the various types of loads that occur in industrial can be classified depending on their variation with time and duty cycle. Okay, so in the industrial applications, various types of loads can be classified depending on their variation with respect to time and the duty cycle. Okay, and this can be specified by a diagram known as load diagram. Okay, so this is the figure which shows typical duty cycle or load cycle, which will give the variation of the load with respect to time. Okay, so let us see the classification of loads with respect to time. So the loads can be classified with respect to time as continuous and constant loads, continuous and variable loads, pulsating loads, and impact loads. Okay. So let us discuss about these loads with respect to time, that is continuous and constant load. So the loads on the motor operate for a long time under the same condition. Okay. So if the load on the motor is operating for a longer time under same condition, just for example, uh, fans in our houses. Okay, so once you turn on the fan and if you set the speed of the fan, it will be running under same condition for longer period of time. So fan can be, you can call it as a continuous and constant load, or the compressor fan. This is compressor fan. Okay, so conveyors, centrifugal pumps. These are the examples of continuous and constant loads. Okay, so these loads will be operating for a longer time under same condition. Okay, so next one is continuous and variable loads. Okay, so these loads on the motor will operate repetitively for a longer duration, but varies continuously over a period. Okay, so they will operate repetitively for a longer duration, but they will vary continuously over a period. Okay, so examples for such loads is this hoist winch. So okay, so this wire is for lifting, and there will be a winch is for moving, sliding on this rod. Okay, for lifting and sliding operations performed by this load. Okay, so it's not performing only one operation, it is performing two operations here. Okay, metal cutting lathe machine. I think I have shown you the lathe machine operation or lathe machine in the earlier class. Okay, so metal cutting lathe machines also for means in order to cut the metal in certain angle, we have to set the settings, and for certain duration of time we will hold the object in our hand, we will cut that machine in that angle. Later on, in order to cut on the other side, we will change the direction of or angular direction or blade, whatever it is there in the lathe machine, and we will rotate the object to the desired angle and will perform the operation for certain interval. Okay, so these loads are the continuous and variable loads. So next is pulsating loads. Okay, so these loads on the motor, which can be viewed as constant torque superimposed by pulsations. Okay, so these loads are viewed as constant torque superimposed by pulsations. Okay, example is crankshaft, load with a crankshaft. Okay, so this is the crankshaft. Okay, so when crankshaft is when loads are connected to the crankshaft, you can see these four piston cylindrical arrangements are connected here. This is the piston rod. Okay, the movement of all these four piston and cylinders is not same because of this shape of this crankshaft. Okay, so these loads will be having a constant torque superimposed by pulsation. Okay, so even tile looms, reciprocating pumps. I don't know if you know about the reciprocating pumps. So if you have had this fluid mechanics subject, I had it in my BTech third year, second semester, of course. Now you people are in third year, second semester. It's in that fluid mechanics subject, different pumps we will be learning. Okay, among those pumps, one of the pump is reciprocating pump. It's a mechanical subject. Okay. Okay, so these are the examples for pulsating loads. Next is impact load. Okay, so these loads on the motor will have regular and repetitive load peaks or pulses. Okay, so the load will increase to a maximum level suddenly. Okay, so I didn't get any image. Okay, for impact load, I don't have any image. For example, okay, but means the load which will increase to a maximum level suddenly. Such loads are known as impact loads. Now let us see the classification of loads with respect to duty cycle. Okay, classification of loads with respect to the duty cycle. So there are actually three basic classifications. One is continuous duty cycle, short time duty cycle, and intermittent duty cycle. Okay, so we can classify the loads with respect to duty cycle as continuous duty cycle, short time duty cycle, and intermittent duty cycle. Okay, so continuous duty cycle means this continuous duty is the duty when on period is so long that motor attains a steady state temperature raise. Okay, so if the motor is attaining steady state temperature range raise due to long on period of the load. Okay, so that you can call it as continuous duty. The motor so selected should be able to withstand momentary overload capacity. Okay, so the motor which is selected for this continuous duty cycle of the load, it must be able to withstand the momentary overload capacity, and this type of motors will have high efficiency because they will be operating almost at full load and also have good power factor. Okay, so the motors which are used for continuous duty cycle, they will have high efficiency and they will have good power factor. Okay, so there are two types of continuous duty cycles: continuous duty at constant load cycle and continuous duty at variable load cycle. So in continuous duty at constant load cycle, the load torque remains constant for sufficiently longer period. Okay, so in continuous duty at constant load cycle, the load torque will remain constant for sufficiently longer period. Okay, example is fan. Okay, fans that we use in our houses. Okay, fans, compressor fans, conveyors. Okay, so they will be having, means their load torque will remain constant for sufficient longer period. Okay, so you can represent it graphically. Where is it? Okay, so this is the torque of the load with respect torque and load with respect to time. Okay, so with respect to time, torque and load are almost constant. Okay, so next one is continuous duty at variable load cycle. So in continuous duty with variable load cycle, the load on the motor is not constant. Okay. So in the case of continuous duty at constant load cycle, load on the motor is constant. But in continuous duty at variable load cycle, load on the motor is not constant, but it will have several phases in one cycle. Okay, it will have several phases in only one cycle. Okay, so you can see here, this is a continuous duty with variable load. This is the load with respect to time. So you can see how load is varying with respect to time. It is not constant. Okay, so selection of the motor for such type of duty involves thermal calculation, which is a difficult task. Okay, so if we want to select a motor for such loads, okay, which will have continuous duty, but the load will be varying, means many a times. That means it will have several phases in one cycle. For such loads, selecting a motor involves thermal calculation, which is very difficult task. Okay, so the motors operating for such type of duties will have poor efficiency and poor power factor. Okay, so the motors which are used for continuous duty with variable load will have poor efficiency and poor power factor. So selection of motor for this type of duty may be based on average power or average current method. Okay, since the thermal calculation is difficult, okay, so that's why if we want to select a motor for such loads which are continuous but which vary many a times. Okay, so for such loads, motors that are used, they are selected based on the calculation of average power and average current. Okay, so next one is, okay, we have discussed till now what we have discussed, continuous duty cycle. Okay, so one we have discussed continuous duty cycle for constant load and variable load. Okay, we have seen two cases in continuous duty cycle. Next one is short time duty. Okay, in this type of duty, the load occurs on the motor during small intervals and remains idle for longer time to re-establish the equality of temperature with cooling medium. Okay, so example is, the best example is mixer. In our houses, you know, in my house, we use hardly for 5 minutes, hardly in my house daily, almost daily, not daily, almost daily. We will use it for only 5 minutes hardly, and we won't use it for throughout the day. Okay, so it is used for very small interval. Okay, the mixer is used for very small interval and it will remain ideal for very long duration of time. Okay, so short time duty is the loads which are connected to the motor, they will operate for very small interval and they will remain idle for very longer time to re-establish the equality of the temperature with the cooling medium. Okay, examples are just for example, mixer, bridges, log gates. Okay, and you can see this is the power with respect to time characteristics for the short time duty. Okay, so we can even say load cycle for the short time duty. Okay, so next one is intermittent duty. After short time duty, let us discuss about this intermittent duty. So the duty in which load on the motor will vary periodically in sequence. Okay, so intermittent duty is, it is the duty in which load on the motor will vary periodically in a sequence of identical cycles. Okay, so periodically the load will be varying, but in identical cycles. You can see here, this is the on time, this is the off time, again this is the on time. This on time is equal to this on time. The maximum value of during this on time is same as the maximum value of this on time for the load with respect to time. So when the load is on, okay, when the load is on, what will happen is the motor heats up for a period of, during the period of T on. Okay, and during T off, the motor will cool down. Okay, so during T on, it is the heating period, during T off, it is the cooling period. So we can calculate the duty ratio depending on this T on and T off values. So duty ratio is given as T on by T on plus T off. Okay, so duty ratio for intermittent duty is T on by T on plus T off. Now, the maximum temperature attained by this intermittent loading can be obtained by using the temperature raise and cooling equations of the motor. Okay, by using temperature raise and cooling equations of motor, we can determine the maximum temperature attained by this intermittent loads. Okay, so you people have to write now in your notes. Okay, I have already written. See, it's not the PDF format, it is written format. So I have spent enough time to write all this. So you people also start writing along with me. Of course, I have already written. As I'm explaining you, you have to write it in your notes and I will check your notes while taking attendance. Okay, now, so let us assume, so our aim is here to determine the maximum temperature attained by this intermittent load. Okay, so let us assume, so just now we have seen the load cycle here. Okay, it has T on and T off and all the T ons will be same, all the T offs will also be same. Okay. So let us assume theta h, theta h1, theta h2 up to theta hn minus 1 are the temperature raises for n times intermittency, and theta c, theta c1, theta c2, theta c n minus 1 is the temperature fall for n times intermittency. Okay, so all these thetas are the raised temperatures and all these thetas are the fall temperatures. Okay. So let T1 is the duration of heating in seconds, T2 is the duration of cooling in seconds, tau n is the heating time constant in seconds, tau c is the cooling time constant. Okay, tau n is heating time constant, tau c is cooling time constant, T1 is duration of heating, T2 is duration of cooling. So theta f is maximum permissible temperature raise of the motor. Okay, as soon as you complete, inform me. Did you complete? Okay. Okay. Now, so during on time, during T on, okay, during T on, theta h is equal to theta f into 1 minus e power minus T1 by tau n. So you know what is theta f, you know T1, you know tau n. Okay. So you just write it down. During T on, the temperature rise, okay, the heating temperature during first cycle of this intermittent load. Okay. Okay, so theta h is equal to theta f into 1 minus e power minus T1 by Tn. You people tau n. So you people write as I am explaining, nothing is there. Okay, so you need not okay worry. So let us assume minus T1 by tau n is minus Tn by tau n is x. Okay, just for simplification. Okay, so then theta h will be theta f into 1 minus e power x. Okay, this is our on time. Assume it as equation number 1. Okay, now during off time. Okay, so during off time what will happen, the temperature will reduce. Okay, the temperature will reduce, so the reduction in temperature theta c, cooling temperature we can say. So theta c is the cooling temperature, so theta c is equal to theta h into e power minus T2 by tau c. So where let us assume minus T2 by tau c is y. Okay, so x is equal to minus T1 by tau n and y equal to minus T2 by tau c. Okay, so you have got some expression during on time, temperature rise, okay, and temperature fall during cooling time. Okay, so theta c and theta h. Now you can this is theta h, isn't it? So you can substitute equation number 1 in 2. If you substitute equation number 1 in 2, you will get theta c is equal to theta f into 1 minus e power x into e power y. Okay, consider it as equation number 3. As soon as you complete, inform. Okay. Now you have got an expression for this cooling, this is the cooling temperature, theta c, that is theta f into 1 minus e power x into e power y. This is equation number 3 now. Now for the next cycle, again it is T on and T off will be there. Okay, in the intermittent cycle, T on and T off will be there. So theta h1 is equal to Tf minus theta f minus theta c into e power x. Okay, so we just multiply these terms and rearrange these terms. You will get theta f into 1 minus e power x plus theta c into e power x, theta h1. Okay, this is the second next interval of on time. Okay, so this is the raise in the temperature during the second cycle. Okay, and now you already know theta c value, that is equation number 3. Substitute 3 in this equation number 4. You will get theta h1 is equal to theta f into 1 minus e power x plus theta f into 1 minus e power x into e power y into e power x. Okay, and whatever multiplications are possible, you do it. You will get theta h1 equal to theta f into 1 minus e power x into 1 plus e power x e power y. Okay, this is during the on time. Now
during off time, that is cooling time, during cooling time, the temperature, cooling temperature is theta C1, let us assume. This theta C1 is equal to theta H1 e power y. You know theta H1, so substitute equation 5 in 6. So theta C1 is equal to theta F into 1 minus e power x into 1 plus e power x e power y into e power y. Okay, so consider it as equation number 7. So till now, you people, I hope you all are writing. So till now we have seen one cycle of on period temperature rise we have calculated, and off period cooling temperature we have calculated. For the second cycle, this slide is, in this slide you can see the second cycle on period temperature theta H1 and off period cooling period temperature theta C1. If you complete, inform. Okay. Okay, so we can, okay, let's go for one more cycle. Okay, next again raise in the temperature during T on and fall cooling during T off. Okay, so raise in the temperature theta H2. This is our third, okay, third cycle. Okay, theta H2 is theta F minus theta F minus of theta F minus theta C1 into e power x. Okay, so you can multiply and rearrange the terms. So you will get theta H2 is equal to theta F into 1 minus e power x plus theta C1 e power x. Consider it as equation number 8. And you already know theta C1, that is your equation number 7. Substitute theta C1 here in equation number 8. This is our up to here, up to, no. Okay, it is also selecting this ex is not there. Okay, ex is it won't belong to theta C1. Okay, so theta f into 1 minus e power x into 1 plus e power x e power y into e power y are the values, means that equation is with respect, that expression is with respect to theta C1. Okay, so theta H2 is equal to theta f into 1 minus e power x plus theta f into 1 minus e power x into 1 plus e power x e power y into e power y into e power x. Okay, now whatever multiplication is possible, you do it and rearrange the terms. You will get theta H2 is equal to theta f into 1 minus e power x into 1 plus e power x e power y plus e power 2x e power 2y. This is what you will get after multiplication and rearranging these terms. Okay, consider it as some equation number 9. Now during off time, okay, during off time, theta C2 is equal to theta H2 e power y. Okay, theta H2 is what? This is equation, this equation number 9 is our theta H2. So now substituting theta H2 in equation number 10, you will get okay. So substituting this theta H2 in this theta C2, you will get this theta F into 1 minus e power x into 1 plus e power x e power y plus e power 2x e power 2y into e power y you will get. Okay, consider it as equation number 11. As soon as you complete, you just inform me. Okay. So similarly, we can further do up to n times intermittency. Okay. So if you go to your nth time, theta hn minus 1, okay, you will get means after performing similar calculations which I have done here in the previous slide. Similarly, if you do, you will get theta h n minus 1 as theta f into 1 minus e power x into 1 plus e power x e power y plus 2 e power 2x e power 2y plus so on up to e power n minus 1 x e power n minus 1 y. Okay, so since it's a big expression, you can rewrite as 1 minus e power nx e power ny by 1 minus e power x e power y into 1 minus e power x into theta f. So theta h n minus 1 is given as theta f into 1 minus e power x into 1 minus e power nx e power ny by 1 minus e power x e power y. Okay, this is our final expression for n times intermittency. Now, as this n tends to infinity, okay, so number of cycles tend to infinity. Okay, so both this e power nx and e power ny will become 0 if n tends to infinity, e power infinity. Okay, you will get 0 as x and y are negative. Okay, as x and y values are negative, as n tends to infinity, this exponential terms will become 0. Therefore, the maximum temperature theta m is given as theta f into 1 minus e power x into 1 minus 0 by 1 minus e power x e power y. Okay, and you can rewrite this expression. Okay, you can rewrite this expression neglecting 1 minus e power x. Okay, if you neglect this 1 minus e power x, it means if e power x is very very small when compared to 1, you can neglect it, then the theta m will be equal to theta f into 1 minus 0 by 1 minus e power x e power y. Okay, this is our maximum temperature with intermittent loading. Okay, you can substitute x value and y value. X value is what? Okay, so what is the x value? Okay, you can neglect it if, okay, x value is what? Minus t1 by tau n, and y value is minus t2 by tau c. Okay, if you remember, it is in, if you have written in your notes. Okay, I can neglect it, or if I am not, if e power x I am not considering very small, then I can multiply it with the numerator of this expression. If I multiply it, okay, I will get theta f into 1 minus e power x by 1 minus e power x e power y. If you complete, inform me.